just wait for a few more people to join. Hi, so I think we'll make a start. My name is Martin Woodcock. I'm chairman of the IET Midlands Power Group. We're joined here today by Tobias Thurnherr from Hitachi Energy. Tobias is going to give us a talk on Potteric Carr, the first rail static frequency converter feeding the UK rail network. So the talk's basically going to give an overview of the Potteric Carr installation, the static frequency converter for railway electrification, how the system compares to conventional rail electrification, and why it's been introduced into several countries over the years. Tobias holds a master's degree in electrical engineering from the Swiss Federal Institute of Technology. He joined ABB in 2007 and has held several positions in systems and R&D, and he's currently the global product manager. So before we get going, I will just say that we will be taking questions at the end. We will also be sending out CPD certificates in an email sometime next week. In order for us to send out the CPD certificates, you will have to reply to the IET feedback. So I believe actually sometime tomorrow you should get an email asking if you attended. If you can just click on that link and acknowledge that you did attend, assuming you would like a CPD certificate, we can then get them sent out. We'll also be sending out with the CPD certificates a link to this recording and also the event slides and maybe any unanswered questions, but we'll see how we do on the questions front at the end. Hopefully we get a chance to answer everyone's queries. Just on questions as well, if you can use the Q&A button in the Zoom to ask questions rather than the chat, because we don't respond to questions in the chat pane, so you will have to use the Q&A button. Okay, right. So I'll now hand over to Tobias. Thank you.
Thanks a lot, Martin, for that introduction. Good evening, ladies and gentlemen, and welcome to the presentation about Potteric Carr. So Potteric Carr is a rail static frequency converter that is feeding the 50 Hertz railway grid from the 50 Hertz three-phase distribution grid. And I mean, hearing that, you might ask yourself, why is a static frequency converter needed if two 50 Hertz grids are connected to each other? And I'm sure that during this talk, this question will be answered along with eventual other questions. To the program of the talk, I've structured it as following. So I will start with an introduction, then go into what is a rail static frequency converter, and then present just one slide about the East Coast Mainline and Intercity Express program. That is actually the program around Potteric Carr. Then go into a little bit more details about the Rail SFC at Potteric Carr, also with a discussion on project challenges, and then in the end close with an outlook and a conclusion. But before really starting now, I would like to thank the IET for organizing this event, for giving us the opportunity to present this interesting project here. So just in the beginning, I would like to say a few words about Hitachi Energy. The reason for that is that I think many people don't know the company yet. It's actually a former division of ABB, the Power Grids division, that was split off and sold to Hitachi. And since a bit more than a year, we are active in the market with the new brand name Hitachi Energy. So we are actually present in more than 90 countries around the world with offices there. And there are 4 business units. This is grid automation, high voltage products, grid integration, and transformers. And grid integration is actually the business unit that was responsible for the execution of this project. And we have customers mainly in utilities, but also in industry, transport, and infrastructure. And we offer product systems, software automation, and services. And looking at the geographies, our business is about more or less equally distributed in Asia, Middle East and Africa, Americas, and in Europe. So that just as a short introduction for those who don't know Hitachi Energy yet. So looking into what is a rail static frequency converter, I will actually start with the conventional concept, the conventional transformer substation feeding concept, which is just a transformer substation. So I think that's a concept that is very well known and that is applied most of the time. And only since a few years, rail static frequency converters are actually used for feeding 50 Hertz railway lines. And a conventional substation, the transformer can be represented by an inductive or by a mainly inductive impedance. And so it's a passive component, and actually the flow of real and reactive power through the transformer is given by the railway load and cannot or only marginally be influenced by the transformer. Also important to say is that different traction substations, they are usually connected to different phases on the 3-phase side. And the reason for that is that with this setup, the unbalanced effects can be reduced. So because of that, neutral zones are needed to isolate sections fed by different substations, because otherwise the power flow between these substations cannot be controlled. So this means that each catenary section that is fed by a different transformer is isolated from the other sections. This means also that the feeding grid potentially sees a bad power factor. So the power factor is basically given by the load and cannot be influenced, or it could maybe by adding additional components. Then the transformer substation is connected to 2 phases only, because the railway system is a single phase system. And this means that there is an unbalanced load towards the 3-phase feeding grid. And this unbalanced load will result in a voltage unbalance. And one option to reduce this voltage unbalance is to connect the substation to a very strong grid with a small short circuit impedance or a high short circuit power, and this is the case for high voltage grids. So typically a transformer rail substation is connected to a high voltage grid. And then with a transformer, we have only very limited control of the voltage on the rail side, and the voltage on the catenary also depends on the 3-phase voltage and on the load. So I say limited control, there can be tap changes introduced, but they are not very fast, and if operated frequently, they need maintenance. So after that, I would like to go into static frequency converters. So you see the schematic of a static frequency converter, a quite simplified one here at the top of the slide, and then also simplified representation of that. So it's basically two controlled voltage sources. It's power electronics, so we can control these voltage sources, and these voltage sources, they are linked by the power, because the SFCs, they have some limited storage capacity, but that's very limited. So the power flowing in one side has to be equal to the power flowing in on the other side. And they have a series impedance from a transformer or from an inductance. And when I say controllable voltage source, so basically we can control the voltage angle, and this means that we can control the active power flow through the converter. And this means that no neutral zones are needed. We can operate these feeding substations with SFCs in parallel, and you can have a whole railway line that is not isolated between the different sections. The second thing that can be controlled with this controlled voltage source is the amplitude of the voltage, and with this we have independent control of reactive power on both sides. I think there are many advantages of rail SFCs compared to conventional substations with transformers. I want to just list the main ones, or go into the main ones here. And I think we can summarize them under two things. One of them is grid code compliance, and the second one is increased flexibility in designing and operating the railway power supply. So grid code compliance, the SFC equally distributes the load on all three phases, so we don't have unbalance. The harmonic emissions on the three-phase side, they are designed to fulfill the requirements. So basically, we get the project-specific limitations, and then we design the SFC to fulfill these limitations. And we can also control the reactive power on the three-phase feeding grid side. Typically, the SFCs, they operate at unity power factor, but they can also contribute to voltage control, to reactive power compensation. And we have customers that basically use this feature to stabilize the voltage of the three-phase grid they are connected to. As said, we don't need neutral zones, and I think this has the advantage that we don't need them, so there is a saving because of that. It also has other advantages connected to that. We have a more stable catenary voltage, so the catenary voltage does not depend on the three-phase voltage. It's independent. It's basically given by the SFC control. And then we can have dynamic control of the output voltage depending on the load. And also because the SFC substations, they can feed in parallel. If there is a train in between two substations here, this train is fed from both sides, and this means that the current from one side is only half of the current that we would have if it would be fed by only one side. And this means that also the voltage drop along the catenary is reduced. So we get a more stable voltage because of that. And this can result in a lower number of substations needed, because a longer distance can be electrified per substation, because the voltage drop is lower. It's easier to recapture braking energy, because if this train is braking, this train is accelerating, the energy can directly be reused. Whereas if you have isolated catenary sections, if there is a train braking here, the energy has to flow back to the three-phase grid and cannot be directly reused in the railway system. The peak power is also distributed on several substations. So per substation, we have a lower peak power. So the substations, they need to be dimensioned for not the same peak power. We have better performance in terms of redundancy, because if one substation fails, then the adjacent substations, they can immediately take over the load, so you will not have an interruption of the supply of the catenary. And last but not least, we have a controlled short circuit current contribution from the SFC. So I mean, SFCs, they have inherently a lower short circuit contribution than a transformer, because they are not overloadable typically by a factor of 2 or 3 for a short time. On the other hand, the SFCs, they can really control how much current they contribute to a short circuit, and this is especially helpful if an SFC is used as an extension of the power supply for an existing line, and the equipment is not designed for a higher fault current. So in that case, the SFC fault current contribution can be set to a value below nominal. So that's just a brief introduction into the main advantages of static frequency converters. I would like to now briefly go into the East Coast Mainline Intercity Express program. So the East Coast Mainline is a railway line in the United Kingdom connecting London to Newcastle. It's a railway line with a total length of 393 miles, 632 kilometers, carrying over 20 million passengers a year. And the Intercity Express was running in the past years, and it basically included the purchase of new Hitachi trains, high-speed trains, and these trains, they needed a depot, which is the main center of excellence for maintenance, cleaning, overnight stabling, etc., for these new Hitachi trains. And this depot is located in Doncaster. You see here with the arrow indicating the position of this depot. And there was a requirement for feeding part of the East Coast Main Line with additional power, and for feeding this depot. So what was the driver for choosing the SFC solution in this project? Basically, as I mentioned previously, conventional rail substations with a transformer, they are connected typically to high voltage, because they introduce this unbalance, and to limit the unbalanced voltage, connection to a high voltage grid is chosen. Now with SFCs, because they equally distribute the load on all 3 phases, we no longer have this problem. And this means that the rail substation with an SFC can also be connected to medium voltage. And this leads to an accelerated permit, because it's easier to get the permit for connection to a medium voltage grid compared to a high voltage grid. It also means a lower cost. So for SFC, for Potteric Carr, we are talking about a 60% lower substation cost because of the connection to 33 kV compared to a high voltage connection. And actually Network Rail, they also claim a cost reduction of the whole East Coast Mainline extension. So that's not only the Potteric Carr project, but also future extensions, a total cost reduction there of around £500 million. So it's quite a big saving that can be achieved with the rail SFCs in this example. And then last is that because of the connection to medium voltage instead of high voltage, we can also have a reduced footprint. Some words about the rail SFC at Potteric Carr. So starting with an overview of the site. So we have the East Coast Main Line here in the middle. Then the depot, the Doncaster depot here just next to the railway line. And then there is the the SFC located here with a connection to the northern power grid substation, existing 133 kV. Then we have here the 25 kV and 33 kV substation for the static frequency converter, and just next to it the static frequency converter. And close to this static frequency converter location, we have the Potteric Carr nature reserve. Here you see a little bit a closer view of the static frequency converter and the connection. And also on this slide is shown what is included in the scope of supply of Hitachi Energy for this project. So it's a turnkey installation, including site preparation, groundworks, and foundations. We have the static frequency converter with the power electronics that is here included in a container that is a little bit hidden between the filters and the bus bars, and then the control and cooling container here. There is harmonic filters on top here and the transformers on both sides. Then we have heat exchangers because it's a water-cooled converter, and the losses there are then transmitted to the ambient air with these heat exchangers. We have installation and commissioning of the whole site included in the scope. And then we have actually this picture here is how to say, the continuation of the picture above, just in another angle. So this here is the heat exchangers that you also see in the picture on the top. So we have the substation here for the SFC with 25 kV air insulated 2-pole switchgear that is containerized, as well as the 33 kV gas insulated 3-phase switchgear. Then we also had the integration to the SCADA system in our scope, the auxiliary supply, and the cable connection to the overhead line and to the depot. And also shown in this picture that was not included in the scope of Hitachi Energy is actually an existing Northern Power Grid substation for 33 kV. That, as I said, was existing already, but was extended to allow this connection of the static frequency converter. The feeding concept, you see here a schematic. So Potteric Carr is normally feeding at the moment the part indicated in black, so between Portree and Doncaster, and also feeding the depot. But it has been designed and also tested to feed this red part additionally up to Redford, then the grey part up to South Kirby Junction and Hambleton Junction, and the blue part up to York. The SFC has been specified, designed, and tested not on the real site, but on a real-time simulator, to also interconnect with other SFCs or with transformers. So that's a mode that is currently blocked. It is not used, but it will be required in the future. This slide shows the customer requirements. I've mentioned connection to 3-phase 33 kV grid and to the 25 kV railway catenary. Converter rating is continuously up to 30.5 megawatt, and then an overload capability up to 46.5 megawatt for up to 2 seconds, with ambient conditions between -25 and 40 degrees during normal operation, and a derating allowed for higher temperature. And just a very brief introduction. I won't go into details here for time reasons, but I nevertheless wanted to listen here the main power quality requirements. So it's basically fulfillment of IEC, EN, and UK norms, ERP 28, 29, and G54-1 for the 3-phase side. And then we have various norm for the railway side. One requirement is also that the SFC should be capable to feed different old and new rolling stock, and I think this is relevant because the old rolling stock partly still uses thyristor converters, and they can have quite a large harmonic distortion. So I think this can go up to a THD of around 30%. And then it was also required to demonstrate interoperability with existing and future railway systems. And I think this is very relevant because the SFC should not disturb track circuit and signaling for the railway system. So that was just a very brief introduction of that, not going into details. The SFC that is used in Potteric Carr is a so-called PCS6000 Rail SFC. So it's a 3-level neutral point clamped converter. You can see the schematic of this converter just for one phase output here. So we have a common DC link, and then this is the AC output of one phase. And you can see here on the right-hand side how this looks in reality. So it's a stack, a semiconductor stack with some passives around it, with the gate units, and also the cooling here of the semiconductors in the middle. So this module here contains 2 phases, so twice the schematic that you see on the left-hand side, and then these stacks, they are integrated in a base frame together with some valve-based electronics, some capacitors, a cooling circuit, etc. And this one is then integrated in a container. We have a common DC link with this technology, and there is a 100 Hertz filter connected to this DC link. The reason for that is that it is with a single phase load, there is actually a pulsating load that has twice the fundamental frequency. So in this case, it's 100 Hertz. And basically, you will see in the DC link, you will see an oscillation with these 100 Hertz. And with a passive filter tuned to 100 Hertz, this oscillation can be reduced. The PCS6000 is based on integrated gate commutated thyristor technology, so abbreviated IGCT. This is a very robust semiconductor with a long lifetime and low losses that I think is very well suited for demanding applications like the rail SFCs. Then it's a containerized solution. So I think the main advantages of this is that we can integrate the converter into the container, make the connections, test them in our factory, and then send the whole container on site. And there is only limited connections that then have to be done on site and tested. So this basically reduces the installation time and the risk. And it's also a compact and competitive housing option. Extensive software tests have been done on a digital real-time simulator before commissioning. So the original control hardware is interfaced with a computer that is calculating in real time the behavior of the power electronics and of the grid. And this allows us to do fast and very accurate testing of the software before going to site. I would like to go into the main project challenges now. So an overview of that. I mean, it's the first 50 Hertz Rail SFC in the UK and also in Europe. It was commissioned back in 2019. Before that, there were some projects in Australia, but not in Europe. The control, as I mentioned previously, has to allow island feeding. So it has to operate as the only source feeding the railway grid, and it also has to be able to operate in parallel with transformers or with other static frequency converters from different manufacturers. Then always important is the fault behavior of the static frequency converter to ensure the continued supply of the railway system, and we have to comply with protection devices to make sure that they can properly react and isolate the fault. And then I think also because it's the first project in the UK, there was quite some need for certification from Network Rail, but then also for other stakeholders. And there was a noise limitation from the nature reserve that is very close by and from a building. So going more into details about these project challenges, I would like to start with control. So as mentioned, the SFC has to be able to feed an island grid and also be able to operate in parallel with a transformer. And for that, we need to have a grid forming behavior of the static frequency converter. So basically, it's not operated as a current source, but rather as a voltage source. And if we look at the parallel connection with the transformer, I think it's important to understand how a transformer behaves. And basically, it's mainly inductive impedance. So we can, in a simplified way, show the behavior of the transformer on this diagram that shows on the y-axis the angle between the single phase and the three-phase grid, and on the x-axis it shows the power that flows through the transformer. So we can show the behavior in an approximated way that is valid, especially around a very small angle, with a line that is crossing 0 here. And the line basically means that if the angle increases, so for example, if the angle of the railway voltage is leading the angle of the three-phase grid voltage, then power is transferred from the single-phase grid towards the three-phase grid. And the more the angle is leading, the more power is transferred, basically. And the slope of this characteristic depends on the impedance of the transformer. Now we want to have a similar behavior of the static frequency converter. So that's why you see here these sloped areas. And there is actually a discontinuation here of the slope on two ends, and this means that the static frequency converter, when it reaches the limit, its limit in power, it just continues to supply the maximum power. The difference of this slope characteristic compared to a transformer is that we can influence the slope. So we can choose the slope and make the SFC behave as we want it to behave. And then we have additional degrees of freedom. We can introduce an offset in the angle as well as in the power. So we can shift the curve in either direction. And we can introduce a dead band here in the middle. And we can choose how big this dead band is. And this characteristic actually gives quite a lot of degrees of freedom to set the behavior of the SFC. So for example, we can choose the dead band in a way that in a certain range, the SFC just supplies continuous power or zero power, and only the transformer reacts to changes in the angle difference. Or we can set the characteristic in a way that the SFC supplies power towards the catenary, towards the railway line, but as soon as power is being or wants to be fed back towards the three-phase grid, the SFC doesn't react until the angle crosses a certain threshold. So there is quite some flexibility in setting the SFC behavior with this characteristic. And then, I mean, depending on how the characteristic is set, this is indicated with 3 examples here. The transformer and the SFC, they share the load. Also in the Potteric Carr project, a phase measurement unit, so-called PMU, was specified and is implemented. So a PMU is a device that is measuring the amplitude and the phase angle of the voltage where it is connected to, and it then transmits these measurements along with a very accurate timestamp of the measurement. And I will just, there are different possibilities to use this PMU, but I would like to just show one example of how it can be used. You can see here in the example that a railway line is fed with a transformer and 2 static frequency converters in parallel. There is a distribution grid, so we have an impedance in the distribution grid. We have an impedance in the catenary between the different substations, and there is also power flow in the distribution grid towards other varying loads. So what happens basically if the impedance in the distribution grid is very small compared to the impedance in the catenary, the power just towards these varying loads, the power flows through the distribution grid. But if the impedance here becomes not much, or is not much smaller anymore than the catenary impedance, then a part of the load will flow through the catenary towards this load, and that's basically not what we want. No, we want to supply the catenary, we want to supply the trains, but we don't want to offload the distribution grid with the catenary. So what we can do now with these phase measurement units is that we measure the voltage phase angle here at the transformer substation. We transmit this signal to the 2 SFC substations, and then we add the angle difference between the angle at the transformer substation and at the SFC substations. We add this difference to the characteristic of the static frequency converter as an offset. And this then means that the SFCs, they behave with their characteristic as if they would be connected to the same location as the transformer is connected. So with that, we can basically prevent that the power is flowing through the catenary system instead of flowing through the distribution grid. So I think in that sense, the phase measurement unit is a very nice tool. The other nice thing is that with this accurate timestamp, we don't need a very fast communication, but we can allow some small delay in the communication. Another very important topic is the fault behavior of the static frequency converters. So basically, I've mentioned in the beginning that SFCs, they have a limited short circuit contribution compared to transformers, which usually easily can have an overload of 2-3 times nominal. The SFCs, they have a much smaller time constant. So this means that they can only supply typically quite a small overload current. Then it's very important actually with static frequency converter feeding that protection relays, they operate properly, and with this limited short circuit current contribution. Protection relays, they are set to monitor the impedance and to detect the fault with the measurement of the impedance and to isolate the fault through that. So this means that the SFC has to provide sufficient current during the fault, and it should not introduce a step in the SFC output voltage when there is a fault. So measures that have been taken for the Potteric Carr SFC were that the SFC behavior was thoroughly tested on the real-time simulator before going on site. So also this fault behavior. And the SFC behavior is actually verified with on-site tests. So basically, real tests were done on site, applying a short circuit and measuring or observing the SFC reaction to that. And you can see here an example of the measurements that were taken. So basically, a fault with a very low impedance was applied for a certain time, and this allowed to observe the behavior at the fault entrance during the fault and also at fault clearance afterwards. So we can see the single phase voltage here and the single phase current of the static frequency converter. And I think what we can observe here is that there is good control of the current during the fault. So it's a stable current that the SFC provides. As I've mentioned, it's very important that the SFC doesn't introduce a jump in the voltage at the beginning of the fault or during the fault. And it's a little bit difficult to show that on the measurements because the fault impedance is so low and there is virtually no voltage remaining. So the way I've indicated it here is, I mean, if the voltage continues with the same angle or without an angle step at the beginning of the fault, this means that the current during the fault should have an offset of 90 degrees to the voltage before the fault, because the fault impedance is basically inductive. And this we can detect it here. The first line here shows the peak voltage before the fault. The second line shows the peak current during the fault, and there is roughly 5 milliseconds time in between, and that indicates this 90-degree phase shift that we want to have. What we can also see is that after the fault, the SFC slowly ramps up the voltage back to nominal. And then a few words about noise limitations. So we have some noise limitations on site. So there is a house close by. There is the nature reserve. We have a limitation to 44 and 51 decibel at the house, and then to 50 decibel in the nature reserve. And at the bottom here, you see the result of the noise study that was done. Basically, what we have done in the project is that the fire protection walls around the transformers, they also have been used as noise reduction walls. And you can see very nicely that the noise emission towards the nature reserve and the building, they are very well damped, and the noise emission limits, they can be met at the specified locations. So I think this example shows that it's quite important to know the emission limits, the requirements early on in the project. Then, because of this first project in the UK, I think quite extensive testing was done. There was a considerable effort into that. And you can see the pictures here on the right-hand side. A lot of tests were also done in the night with different trains that were reserved for testing the SFC behavior. The reason why the tests were done in the night was that they wanted to ensure that the railway system is not disturbed during daytime when it's normally operating. So there were very extensive tests done, and I'm very happy that the PCS6000 Rail SFC has received the official certificate of acceptance from Network Rail, so fulfills these requirements as the first SFC in the United Kingdom. With that, I come to the end of the presentation. So I would like to close with an outlook. I think we have seen that SFC technology for feeding railway lines has clear advantages. So we have a lower cost of electrification, faster execution, and we also have a lower substation footprint. And this means that further SFCs are currently being built for the railway electrification in the UK. And I think there are also additional SFC projects that are in a planning stage. And then in parallel, other rail SFC projects, electrifications are also being executed in other European countries. So we have in Czech Republic commissioning that is being completed on an existing line that has been electrified in Otrokovice, Rikovice, where 3 15 MVA SFCs have been supplied. And then another ongoing project in Lithuania, where for the first time a line with a total length of 376 kilometers is electrified with rail SFCs, 50 Hertz. And for that one, 8 times 45 MVA SFCs are supplied. And to conclude, I think the first rail SFC in the UK has successfully been put into operation in Doncaster, and it's fulfilling the strict requirements, and with that it has proven that it's a valid alternative to conventional transformer substations. And I think I can say that with this Potteric Carr SFC, Hitachi Energy has paved the way for future SFCs feeding the rail network in the UK. So with that, I conclude my presentation. You can find my details on this slide. Thanks a lot for attending the presentation, and I'm very happy to answer your questions now, along with my colleague, Subrata.
Thank you, Tobias. That was a truly fascinating presentation there. It's amazing to me what can now be done with power electronics, whereas historically you'd be looking at a 400 kV transmission voltage connection for a traction feeder station, and we're now down at a distribution voltage level. So we're now going to take questions. We've got quite a lot of questions in the Q&A. We've got about, I think we've got about 28 currently. So I'll hand over to the Midland Power Group Secretary, Dr. Gould, who'll run through the questions. We've also got Sabrinta Ghosh on the call. Hopefully I'm pronouncing that right, Sabrinta, who was also the CEM for the Potteric Carr project.
Okay, thank you, Martin. We'll just go through, as I say, we've got 29, so we'll start off at the top and just work our way down. So Devang, we've got, what challenges did you face when pushing for FSC solution over alternatives for ECML?
Yeah, I think, Chris, there's a question before that, isn't it, from Phil?
Not that I can see on mine. That's
okay. Bear with me a second. Oh, okay, he's actually replied, I've answered my own question, so that's okay. Right, okay, so, I mean, yeah, going back to Devang's question, what challenges did you face when pushing the SFC solution? over alternatives for ECML. I think Network Rail at that time were looking at alternative solutions, to be honest, at that time. And the Potteric Carr site itself was a nature reserve. So we had to remove quite a bit of vegetation to enable us to install the SFC, if you like. At that time, Network Rail had engaged with a consultant to do some preliminary work. And the consultant was already involved with the project that we mentioned earlier on in Australia, where the SFC was successfully installed. So that's how this all started, if you like. Now, challenges are, of course, it's a change to the normal railway infrastructure. And one of our main challenges was to prove that this technology will work in the UK. So I don't know whether you know about the ESRP, which is the safety review panels. We had to do some presentations and discussions with them before this project did actually become a reality. So the biggest challenge for us was to try and convince the Network Rail stakeholders, shall I say, and it's not one, there's probably about 15 of them stakeholders that we had to deal with for this project to convince them that this technology will work. So we worked quite carefully. Instead of trying to feed the SFC to the whole railway lines, we decided into a small section, shall I say, which is why Potteric Carr was chosen to feed a small section between Pottery and Doncaster to see how that works. And as Tobias said earlier on, we had to run trains overnight to see whether the SFC actually behaves the way it should be behaving. So that was our initial challenge, shall I say. The other challenges are obviously project related in terms of trying to convince different Network Rail stakeholders, especially cybersecurity, EMC, noise, different stakeholders to convince that this technology will work, because the Network Rail projects, we normally have external bodies like the ASBOs, etc., to convince them. So that was the initial challenge, but again, the testing regime for the SFC was quite detailed, shall I say, in order for us to get the sign off.
Maybe if I may add one thing, I mean, this might not apply for the Potteric Carr. Actually, I was not involved in that in the beginning, but often when discussing SFCs, I think what the question we hear is that I mean, SFCs are more expensive than transformers, and if you compare an SFC with the transformers. And transformer, this will always be the case. Now the substation is more expensive, and often the other system aspects, they are not considered when doing a comparison of the SFC solution and the transformer solution. So I think it is very nice to see that in the UK for the Potteric Carr project, this was understood and the analysis was really done on a system level, and then it was concluded that an SFC is more optimal.
Thank you, Tobias. Thank you, Subrata. So we go to the next question, one from Andrea. Is the output transformer there just because all design was done for 15 kV, 16.7 hertz railways? Could we get rid of the output transformer if we design the FFC for a 25 kV output? Petru has provided an answer on there. I don't know if you have any further comment to add, Tobias or Subrata.
Actually, I didn't see the answer. Basically, the SFC has, I mean, there are technologies to leave away the transformer, basically. With the PCS6000, we have an output voltage of around 3.3 kilovolt. And this means that a transformer is needed both for 15 and for 25 kilovolt. And I think the PCS6000 is still a very good technology for rail SFCs. So that's the reason why we continue to use it for this application.
Okay, thank you. We move on to M. Bartley. What specific protective devices does the FFC have for open and short circuit IGCTs? Have there been any technical performance issue with these protective devices? And if so, how were they overcome?
There are no protective devices for opening short-circuited IGCTs. And I think the design philosophy there is to use a device that is very, very reliable and that is powerful. So we have a low number of devices. And with this design philosophy, we can supply a converter that has a very good reliability. And I think the experience at Potteric Carr shows that the PCS6000 basically is a very reliable converter.
Okay.
I don't know if this fully answers the question. I mean, the IGCT, when it fails, you don't have to protect it. No, it makes a short circuit, and it's mechanically protected, so it won't explode. You don't need to protect anything around it. Yes.
Okay, great. Thank you for that, Tobias. If we move to the next question, I think it's Ray now. If the FSC has to come out of service, is a conventional backup supply provided?
I think that's also a question of how the railway operator designs his power supply. So I think it's common. It's required to have some N-1 redundancy. So if one element feeding the railway network fails, then there needs to be enough power to feed the railway system and to ensure normal traffic. And this can be done by having 2 SFCs per substation, by having more substations than needed, and allowing any of the substations to fail. So there are different concepts for that. And yeah, maybe Subrata, you can comment for Potteric Carr.
Just to add to that, Potteric Carr being the first project in the UK, I mean, the plan was to have 1 SFC, but in theory, going forward, it appears that Network Rail do understand that there'll be an N-1 redundancy. So all the SFC projects that I'm aware of that going forward, they do have 2 SFCs, 1 as a backup. But it's a good question. If Potteric Carr SFC actually fails, the SFC looks after itself anyway, so it controls the breakers upstream and downstream. If there's a problem with the SFC, it trips itself, it trips the breaker upstream and downstream. And what happens, the 25 kV switchgear then works as a TSC, which is an in and out power feed. So that continues to power the railways. The power comes from the adjacent substations.
Okay, thank you. So if we move to Andrew Shepherd, how do the operating losses electrical compare to a conventional transformer, and what would be the anticipated life considering the semiconductors?
Well, to the first question, the losses, they are higher than a transformer, obviously, because you have the power electronics, you have a transformer on both sides. However, on the other hand, the losses can also be reduced with an SFC with a more stable voltage. So you will have lower currents in the catenary, and this reduces the losses. And then, as I've shown, also the braking energy can better be reused with an SFC. So I mean, it's on one hand it's a little bit higher losses because of the power electronics, but then you save on the system losses. And I think with that, the higher losses with an SFC can be compensated or overcompensated. The second part of the question, so we design our converters with the main parts, the power electronics, the main passive components for a lifetime of, let's say, 40 years. And I think we have made very good experience so far. So I think the SFC can have a very long lifetime.
Yeah, so in addition to that, there are some key components that we hold as spares on site anyway. If there are some key components that we believe that will have a shorter lifetime, we actually are storing them on site. So far, it hasn't occurred yet, but again, we ensure that there's a reliability target that we need to achieve. So we have to ensure that that reliability target is achieved. Because in addition to the actual project, we do have a 7-year long-term service agreement with Network Rail as well, which is currently ongoing to ensure that we maintain the reliability figures that we had promised at the start.
Okay, thank you. So moving to the next one, Malcolm Plaster. With all power electronics there is, by their normal switching processes, generation of transients with electromagnetic fields extending into the radio frequency region, what measures are taken to conform to international standards, and have HF noise levels been taken before and after putting into operation?
Absolutely. I mean, I'll probably answer the second part of it. In terms of noise levels, Malcolm, we have definitely gone there and done our initial survey before even the site was built. And then after the SFC was put into service, we had to do testing on the noise levels. We had to, once we did the test train runs in the night time, we ensured that the noise levels were within the limits that we were asked to comply with. So that element was done. In terms of the EMC as well, again, the same thing. We did EMC base arrangements, base tests before the site was even started, if you like, and then afterwards as well. So these were all part of, shall I say, the approval process that we went through Network Rail to ensure that we are not making the environment any worse than it was before.
Okay. Yep, okay, we'll move to the next one then. Omar, what are the disadvantages of FFCs compared with conventional feeder stations?
Okay. That's a good question. It's a difficult question, because if you look at the overall, so there are two things. One is technology and one is commercial, right? Decisions, a business case, shall I say. So if you look at the Potteric Carr situation that we were in terms of the power that is required for the depot and the increased power required for these new electric trains, a business case was created to compare between having a national grid 400 kV substation built in some area, obviously not Potteric Carr because it was a much limited area, as opposed to having the Potteric Carr DNO supply. So in terms of that, commercially, it was always a winner in terms of SFC. As I said, the challenge was to introduce this new technology into a very conventional railway system in the world. So that I mean, it's very, I'll struggle to actually find any disadvantages of the SFC. One disadvantage might be for the maintainers, shall I say. The maintainers obviously are not used to new technology. They're used to the traditional substations. They know what to do exactly when they go out to site. But we had to train, of course, a number of maintainers to ensure that they understand how this works. Having said that, as I said about the long-term service agreement, we have dedicated Hitachi Energy engineers who are conversant with this technology, who are sitting in the UK. If there's any issues, they're on site 24/7.
Great, thank you for that answer. Tom Gibson, I think, is the next question. How does the cost compare to an equivalent 132 kV transformer connection?
Well, I think the indication that I've shown is that the substation cost with an SFC was 60% lower compared to high voltage connection.
Okay, if that's what it's.
Yes, in addition to that, I mean, in the UK, 132 kV level effectively is getting towards the high voltage level, to be honest. The whole idea of the SFC was to utilize a 33 kV connection, if, which makes it much more cheaper. But yes, an SFC can be connected to a 132 as well. But again, getting a 132 kV connection also involves 132 kV switchgear, which is much more expensive, shall I say, than a 33 kV switchgear.
Okay, we'll move to the next question. Are there any challenges introduced to the wider power network by requiring all three phases from a distribution line compared to a single phase?
Sorry, I just want to read that question again, Chris.
Yep, so it's, are there any challenges introduced to the wider power network by requiring all three phases from a distribution line compared to a single phase?
Yes, so in terms of the SFC technology, I mean, an overall system study was carried out by Network Rail, shall I say. So there is a model, shall I say, of the East Coast Main Line, where we had provided our input from our side, from Hitachi Energy, in terms of the SFC. So in terms of any issues, that would have been picked up through simulation studies beforehand. But for example, this one, or SFC technology, did not show any adverse effect on the wider network, shall I say. So the SFC green signal, shall I say, from Network Rail wouldn't have gone across unless those simulations went wrong.
Thank you. Bally, how does commissioning work with expertise required for new technology like FFC? Did Hitachi come on site or utilize remote access?
We went on site, yes. So people from our center of competence were there for commissioning the static frequency converter, and I mean, we are available through remote connection if there is a problem that needs support from an engineer from our center of competence. But commissioning, yes, is done with the people from our center of competence.
Absolutely. I mean, the commissioning was done in conjunction with the guys from Switzerland and our UK commissioning team together. The SFC is monitored 24/7 remotely from Switzerland, which is why we have the long-term service agreement. So they can actually log in from Switzerland and actually check the behavior of the SFC and what went wrong.
Okay, thank you. So we have a question from Dave Sinclair. Dave says he's a non-power engineer, but he asked the question. But if a train consumes 5 megawatts, isn't there a rather low limit to the number of trains that Potteric Carr can concurrently power? I'm sure I've missed something, but not sure what. How many trains is the limit? There is an answer from Matt, but if you can give your answer, that'd be great.
I'm actually trying to find the question. And what was the answer there from?
There's Dave Sinclair, and Matt said 5 megawatts is the accelerating power. If you consider coasting, deceleration, and regenerative braking, then 30.5 megawatts could power quite a large section with quite a few trains.
Yeah, so the power requirement, if you like, for Potteric Carr at that time was about 30 megawatts, shall I say. You've got to remember, we were talking about the depot as well. So the depot, which is probably around 2.5 kilometers away from Potteric Carr, the depot that Tobias showed earlier on in the map. So we are also powering the depot at the same time, plus the railways as well. So the requirement, shall I say, was 30.5 megawatts to power up the depot, plus any trains that are running past at that time. So we have recently, I would say, there was a plan to do another SFC in Grantham, which is a bit down south, which is about 27 kilometers away from Potteric Carr. We did a trial test to see whether the Potteric Carr SFC can feed all the way down that 27-kilometer route. And it actually successfully did that, which is why one of the SFCs at Grantham project got scrapped, because the Potteric Carr SFC could do that.
Great, thank you for that. Question from Oliver. From the feeding diagram, it appears that the FFC is only operating in island mode. Are there any plans to trial double end feeding with another FFC as part of the PSU?
Absolutely. I mean, that's the plan. I mean, because there's a big gap, Oliver, between the Potteric Carr SFC being commissioned in 2019 October, and the next one coming up is in Hambledon Junction, which is being carried out by Siemens. So the SFC that we have designed is currently for an island mode, but it is capable of going into parallel mode as well. So that is currently being disabled, of course, till the Hambledon Junction SFC comes on board. So at some point in time when Hambleton Junction is ready, there will be a plan, shall I say, or a testing regime to ensure that the two SFCs talk to each other.
Okay, thank you. I've got a couple of questions on here. I'm not too sure if that's a formal name or an informal name on there, but I'll ask the question. Sorry if it's your formal name. What is the typical distances between conventional substations? How much can this be increased with FFCs?
I think that's very difficult to say because it's different for every railway line now, depending on the load, on the traffic. So I think we have done some not real simulations, but example simulations with a imaginary railway line. And I think the distance there between substations could be increased by some 30–40%. Yes, but it's very difficult to give a general indication about that.
Okay, I've got another question from the same attendee. How clean is the 50 Hertz rail output and THD content?
I don't know the exact THD value for this project, but I mean, as I said, it's the SFC is designed to fulfill the project specific emission limits. So the THD is very low.
Okay. Anonymous attendee. So this is a question here. A major problem with complex power electronic systems is obsolescence, parts and control modules not being available, software becoming obsolete, or the technical skills lost to people leaving or retiring. How long does Hitachi support the FFC for, and what is the service life?
Well, we have some SFCs that have been in operation already more than 20 years. We've also executed control retrofits. So I mean, the control hardware at some point of time becomes difficult to maintain. But as I said, the power electronics is designed for a longer lifetime. So this means that we typically offer our customers to replace the control hardware, and with this we can again make the SFC work another 20 years. So I agree that this is a challenge, but we do. I think for us it is very important that our converters they can stay in operation, and that we support our customers also retrofitting the parts that need to be replaced.
Okay.
Yeah, just in addition to that, again, as I said, we have this long-term service agreement for the next 7 years for Potteric Carr. So we tend to monitor anything that needs to be upgraded. For example, you know, the simple things that we have the HMI, for example, in the substation, we got 3 PCs there. They are running on Windows 10, for example. If that requires an update, that will be updated at some point. You know, small things like that. I can understand. It's a good question. And obsolescence is always something that we have considered, and we have definitely contributed towards that.
Okay, thank you, Sparta and Tobias. You've got a lot of questions.
It's good to have questions. Yes,
definitely. Yes.
Clive Kessel, are there any implications for 50 kV auto transformer arrangements? Also, the use of booster transformer to reduce inductive interference to adjacent telecom circuits.
No, actually, the SFC can feed the system as a transformer, be this 25 kV, be it 50 kV. There is no difference there.
Okay, thank you. One from Phil. Why do you have both 25 kV and 33 kV at the Doncaster FSC station? Is there a legacy system supplied at 25 kV and the SFC supplied by 33 kV?
I think Phil has already answered this question. In the response, he said, I've answered my own question. Is that correct? Is that the question? The first, yeah. So this is Phil's question. Why do you have both 25 kV? Yes. And I think he's responded himself saying, I've answered my own question.
Oh, has he? Okay. Oh, yep. Sorry. Yeah. I can see that one. Fine. We'll move to the next one. Noel, What are the technical and economic benefits of connecting an FFC at 33 kV versus a higher voltage, say 132 kV?
I mean, again, as I think I talked about this earlier on, if you want to connect on a 132 kV supply, that's absolutely fine. But what you need is a 132 kV switchgear. So if you compare that with a 33 kV switchgear, you straight away have economic benefits to have a 33 kV substation. A 132 kV switchgear will be much bigger, shall I say, will require more space. Whether it's GIS or AIS, it doesn't matter. A 33 kV is a much more small, compact, medium voltage switchgear. So straight away, that's an economic benefits. In terms of technical benefits, there is no technical benefits. We can connect to any supply we want to.
Okay. Alan, it seems to me that the FFC allows conversion of voltage and phase as well as frequency. Is that correct?
Yes, that's correct. Yes.
Absolutely.
So SFCs have been used for a long time for feeding 16.7 hertz railway lines where a frequency conversion is needed.
Yeah, unfortunately, the word is SFC, which is a static frequency converter, but we are not using the SFC as a frequency converter in the UK. It's just being applied to convert a three-phase voltage to a single phase with the same technology.
Okay. So we've got Colin, there's two comments on here. Do you need to have a communications link between multiple FFCs to ensure accurate load sharing along a track section? The FSC slope load response would automatically compensate for this.
We don't necessarily need it. No, I mean there are different ways to control the SFC. If it's operated together with a transformer, I think I've shown this phase measurement unit, then this setup actually allows to prevent power to flow through the catenary that should flow through the utility grid. So I mean, this is it's not how to say a direct communication link giving reference values. So the timing requirements are not that strict. It's just the transmission of this phase angle and the timestamp.
Okay, thank you. Bally, I'm aware of feeder stations supporting IEC 61850, but is the FSC local control system also IEC 61850 based or proprietary?
We can offer a IEC 61850 connection to the SFC. There are other protocols supported as well.
Okay.
Yes.
Omar, how does the FFC behave against high inrush? And if two FFCs are operating in parallel mode with one FFC losing its 33 kV supply, would the second FFC start feeding the 33 kV dead network?
I think that's probably a question that can be answered by the next project, because we're only working with an SFC at the moment. But answering that question, yes, I'll probably give you an example. There was a voltage fluctuation on the 33 kV side, high voltage from Northern Power Grid. The SFC works to a certain limit anyway. And if that exceeds that limit, if it goes beyond that limit, the SFC just takes care of itself and shuts itself down. So the SFC does take care of all of itself. But going back to your question on the dual SFC, we obviously the Potteric Carr SFC is a single one. But ideally, if we had two SFCs operating in parallel, if one shuts down, the other will look after itself.
Okay, thank you. Phil, were any real-world measurements taken to validate the noise simulation that was done? If so, how accurate was the simulation?
That's a good question. I probably have to ask the noise consultants here. But yes, I mean, real measurements were taken. As I said, we had overnight trains running, shall I say. I mean, that again, the testing regime was quite rigorous, to be honest. We had, we had to apply for various outages, etc. And we had 2 nights, if you like, of testing 3 times, I think, from memory. Where we had to do all our EMC noise measurements at the same time when the trains are operating. So a lot of these measurements had been taken, recorded, put into the safety case, and obviously issued back to the client. So yes, a lot of live measurements had to be undertaken, especially this being the first one in the UK.
Okay, thank you. Alan, the fault current trace appeared to show the converter on no load prior to the fault. Were any tests done on full load prior to the fault?
No. We didn't do a live test as such with full load, if you like. So the only testing we did was with test trains running overnight.
Okay, thank you.
I mean, I think the tests were done on the real-time simulator with a full load. So I mean, there it's very easy to do these tests now. And I mean, what helps is if you compare the behavior of the fault with no load on the real-time simulator and on the real side, then you can somehow validate the correct behavior of the real-time simulator. But I think it's more complicated to do the tests on site with the full load, and that's probably the reason why it was not done.
Okay, thank you. Question from Glenn. Conventional transformer feeder stations are rated for large short-term overloads as typically experienced in perturbed train working conditions. Sorry, I can't pronounce that one. Perturbed train working conditions. SFCs are rated for a 2-second peak overload. Is this likely to result in a risk of total shutdown of train running in such circumstances?
I would say that what is typically done is or what has to be done is a study that defines the peak load that is observed for a certain railway line, and this study then gives the input of the SFC dimensioning. And this also defines this requirement of a 2-second peak overload in the case of Potteric Carr. So I think with this requirement, the SFC is sufficiently designed to reach the peak. I mean, should a situation occur where more load is required, what the SFC will do is that it will reduce its output. It will not just trip, but will reduce the output. And I think this will result in the locomotives also reducing their load if it's just a very short temporary peak. So I don't think this will result in a shutdown of a train running.
Okay, thank you. David, apart from 2 examples in the presentation, how widespread are FFCs? It's
not very new, but relatively new concept for 50 Hertz railway feeding. So there are a few SFCs in Australia. There is the one in the UK. There are these 3 in Czech Republic, and additional ones currently being built. However, it is a concept that is very well known from the 16.7 Hertz world. So Switzerland, Germany, Austria, Sweden and Norway, and parts of the US that have 25 Hertz railway lines. And they need some frequency conversion, and static frequency converters have been introduced some, I would say, almost 30 years ago. And so the technology is very well known, basically.
Thank you. We're getting close to the end of the questions, so it's not too Glenn, are SFCs adequately rated, tolerant to cope with numerous short circuits as typical on most railways with reduced overhead line clearances?
Yes, I mean, the short circuit is not kind of using the SFC now. It's not being damaged each time it sees a short circuit, and then after 100 it just breaks down. so I think the answer to this question is yes. It can handle a large number of short circuits.
Okay, thank you. Caitlin's question's been answered. Noel, in terms of reliability of the converters, how many converters or module failures the SFC can take before it shuts down?
This is a question of design, and I think, as I've previously mentioned, I mean, there are different concepts. Now you can design a component to have some redundancy in it, or a unit, you can design it to have some redundancy in it, so that it allows to continue operation with a failed component. You will probably not have redundancy in every part of the system. So there are some SFCs that allow modules to fail and they continue to operate, but then probably if you have a problem in the cooling system, in the switchgear, whatever, the unit will fail. The PCS6000 does not, the one used at Potteric Carr, it does not have redundancy in the power part. And the reason for that is that a little bit different design philosophy, so to really reduce the number of components to the minimum and take components that are very reliable. And with that, I think you can achieve an equally good performance in terms of availability of the converter.
Yeah, absolutely. I mean, we were given a reliability target really by Network Rail. And based on what we have designed so far, that reliability target was achievable, shall I say, with what we had. If the reliability target was a bit more stringent, then we might have considered, for example, redundant components within the system, but it wasn't required because we were achieving the reliability targets given to us at the start of the project.
Okay, thank you. Just the last couple of questions. Is Potteric Carr being operated in bidirectional mode?
Yes.
Okay. Graham, does the Potteric Carr SFC have links to the 25K feeder protection devices, IEDs, to actively control the fault current in the event of a fault? The benefit will be reduced infrastructure damage.
Yes, so basically as I said, the SFC controls the breakers, the incoming breaker from the 33 kV switchgear from Northern Power Grid side, and also controls the breaker on the 25 kV switchgear, the incoming breaker. So the IEDs on the incoming breaker are all talking to the SFC control system.
Okay, thank you. And the last question was there, just a confirmation, you do get CPD certificates for attending the presentation.
You can answer that.
The attendees do. So I think that brings our questions to a close. I'd just like to personally thank both the speakers. You've done a lot of questions, and I think we've never asked speakers so many questions in a session before without answering them outside. So thank you very much, Tobias and Subrata, for that.
Thanks a lot to you for moderating.
If there are any other questions that we failed to answer or we missed, Chris, you're probably going to, or Martin, you're going to send that across to us at some point.
We will, yes.
Thank you. I saw a question from Stephen Locke, who I know from the past. So I don't think we answered that question, but perhaps you can gather that and send it to us, and we'll answer that later on.
We will do, yeah. Any questions that weren't picked up, we'll send those across in an email. Right, yeah. So thank you, Tobias and Subrata. That's very interesting talk on the Potteric Carr static frequency converter. I know we're very tight for time. I did just have one question myself. How difficult was it to actually obtain a 33 kVA supply at the MVA requirement? Because obviously it's a lot of current that you required.
Well, I don't think it's a lot of current to be calculated on a 33 kV with a 30.5 MVA. I mean, the
500 odd amps, isn't it? Yeah.
Yeah. So
yeah.
I mean, for an MV, it's okay. I mean,
Yeah.
we normally deal with 630 amp breakers, so I don't think that was too much of an issue. I think Network Rail had already planned this, and the switchgear, fortunately, at the Northern Power Grid end was an ABB ZX 1.2 GI switchgear. So they had a separate project for an NPG to extend that by 2 circuits to feed Potteric Carr. So
Okay.
basically, we got 2 circuits into Potteric Carr as a redundant circuit into the 33 kV incoming substation at
Oh,
Potteric
right.
Carr.
Okay. Yeah.
So yeah, so if one circuit fails, the other can actually.
You've got a back. Yeah.
Yeah, we got redundancy there in terms of the incoming supply.
Very good. Okay.
Yeah.
Okay, right. As we said at the start of the presentation, within the next day or so, attendees on the call, you will get an email just asking whether you attended. If you would like a link to this recording and your CPD certificate, if you could just reply to that email and say that you've attended. So on behalf of the Midlands Power Group, and I'm sure everyone on the call, I'd like to thank you, Tobias and Subrata, for your thoroughly entertaining presentation. Very good, thank you. Yeah. One last thing before we close, the Midlands Power Group have got an event on the 6th of December, which is from Birmingham University. It's regarding hydrogen and its use for train propulsion. It's available now to sign up to on the IT events site. For anyone in Birmingham, I would encourage you to come into Austin Court. You even get some free food, so yeah, all good. Okay, thank you very much.
Thank you, Martin. Thank you, Chris.
Thank you. Cheers.
Thanks a lot. Yes. Have a good evening.
And you.
Bye.
Bye-bye.
Bye.
Bye. Thanks.